All right, today we're putting on our detective hats. We're going to investigate a sneaky problem in the world of research, a kind of silent saboteur that can make perfectly good data go bad and can lead even the smartest researchers to totally wrong conclusions. So let's crack this case.
So picture this. You've just crunched the numbers on your latest project, and the results? They're beautiful. All the relationships are super strong, the model fits just perfectly. Almost too perfectly. You ever get that feeling? Could there be something else going on behind the scenes, some hidden force that's just artificially boosting your findings?
Well, that hidden force actually has a name, and it's the prime suspect in our investigation today. It's called common method bias.
So what is this thing exactly? Put simply, it's a glitch that comes from how you collect your data, not from what you're actually studying. Think about it. Maybe it's the way a question is phrased in a survey, or maybe people are just trying to give the answers they think you want to hear. Stuff like that can create these fake connections in your data, basically contaminating the evidence before you even get a chance to look at it.
To really see how this culprit works, we're going to look at a really cool experiment from a paper by a researcher named Ned Koch. He set up what you can think of as two different crime scenes. One was totally clean, and the other was contaminated.
This is the model he used for the experiment. It's pretty straightforward. It suggests that a company's collaborative culture influences how much they use collaboration tech, and those two things together lead to a competitive advantage. Seems like a simple case, right? Or so you'd think.
Now, using that model, he created two data sets. The first one, the clean data, was designed to be perfect, absolutely no bias. But the second one, the contaminated data, was an identical copy, except this time he deliberately baked in a dose of common method bias.
And bam! Look at the effect of that contamination. The link between collaborative culture and tech use in the clean data was about 0.45. But in the contaminated set, that same relationship jumped all the way up to 0.625. That is a nearly 40% artificial jump. This is exactly the kind of thing that leads to false positives, where you end up claiming you found something important when it's not actually real.
Okay, so we know the contamination is in there. The next logical step is to run the standard diagnostic tests to find it. But this is where the mystery gets really interesting, because the usual detective tools, they completely miss the problem.
First up, the convergent validity test. This is supposed to check if the survey questions for a concept are all strongly related to each other. And look at this. Both the clean and the contaminated models pass with flying colors. In fact, the bias actually fools the test and makes the contaminated model look even stronger. The test just sees all that shared error as a good thing.
All right, what about the next test? Discriminant validity. This one checks if your big ideas are actually distinct from one another. And again, guess what? Both models pass. The bias actually inflates everything at once, basically hiding in plain sight and fooling the test completely. And this is the real kicker. The model that we know is contaminated looks perfectly healthy according to the two most common checks in the book. It's like a suspect with a rock-solid alibi. The bias is there, we know it is, but our traditional investigation has just hit a total dead end. So what do you do now?
Well, when the old methods fail, you gotta bring in a specialist. And in our case, our new detective is a much more powerful and comprehensive way to root out these kinds of hidden problems in a model. It's called the full collinearity test. And instead of just looking at little bits and pieces of the model separately, this test looks at the entire system all at once. It's searching for something called collinearity, which is just a fancy way of saying an unhealthy sameness, where your variables are way too similar to each other. It gives you a score for each variable, called a variance inflation factor, or a VIF. So, let's unleash this new, more powerful test on both our clean and our contaminated datasets. Let's see what it finds. And whoa, the results from this test tell a completely different story. Just look at the VIF scores for the clean model up top. All of them are pretty low, well under 2. Everything looks great. Now, look at the bottom row for the contaminated model. The scores are all higher for sure, but there's one that really jumps out. You see it? That one right there, 3.720, the one for competitive advantage. This number is our smoking gun. It is the one crucial clue that the other tests completely missed. But what does it actually mean?
Here's what it means. There's a widely accepted rule of thumb, a threshold for when this sameness becomes a serious problem. And that threshold is a VIF score of 3.3. Our score of 3.720 is clearly over that line. The full collinearity test has sniffed out the contamination. Case cracked. So, why does all this detective work matter? Because finding this bias isn't just some abstract academic game.
It's about protecting the integrity and the reliability of research itself.
So, let's just recap what we've learned. First, common method bias is a real danger that can make you think you found something amazing when you really haven't. Second, the standard checks that you might be relying on, well, they often aren't strong enough to catch it. And finally, the solution is to use a more powerful tool, like the full collinearity test, to make sure your model and your findings are actually legit.
You know, some researchers have argued about this for a long time. Is common method bias a huge deal, or is it more of an urban legend? Well, as we just saw, it can have a dramatic and very real effect. And that leaves us with a pretty haunting question, doesn't it? How many published findings in all fields of science and business might be built on this same shaky, contaminated foundation? It's a question that reminds us to always keep digging. Thanks for joining the investigation.